engineering. Myself, I learned I learned and also rapid having last week what we learned this value ordinary differential. So before moving ahead, let's once again what we learned because it is something that we are going to dive. We first learned before ordinary differential, learned how to write RK2 method, method, and we learned how to use D45 and solvers. Then we solved simultaneous ordinary differential. We also learned how to write. Let's go through our last week's problem and then we go ahead with the problem of CSTRs. So let's take this problem first. Let the following system linear ordinary differences x dt is equal to 5, dy dt is equal to 5. Initial conditions are t is equal to 0, x is equal to y is equal to, and we are supposed to the value of 10. We are supposed to solve this problem using two solvers. Let's do that. I have opened my MATLAB. Please write one live script. Let's try to revisit the problem the way we did last time. So, then is first dx dt equal to y, and secondly dy dt equal to 0. So, let's write down the here all, and then we will apply CSTRs. Then, okay, let me write down the equation. The first equation is dxy dt is equal to y, and second equation is dy by dt equal to dy by dt is equal to minus 2x minus dy into x minus b into y. So these two equations we need to solve and we need value at e is equal to 10. So I will specify my time span from let's say 0 to 10 because we are supposed to give a value at is equal to 10. And initial guess is given to us as not initial guess, initial values when t is equal to 0, my first variable x is equal to 1. So I will be writing y0. When t is equal to 0, x is equal to 1. And my t is equal to 0, my y is equal to. These are all initial values. Correct? Now let's first write down the function for solving this. Okay. So let's see how did we write it. So we wrote it like this that I define my function dy, the value that I'm supposed to find using the name of the function ODEs and time, particular time instant, and that potential. As we are having two equations, I will write it down as my first equation dy of first equation. So we have two equations. I will write first equation that is equal to y. So instead of writing y, we can write, so we have two variables like x and y. So y I am taking it as y of Or else what you can do, y of 1 is equal to x and y of 2 is equal to y. So my first equation I can my second equation, second row, first column, that is equal to minus 2 into x minus we is remember that we should not place here. Okay. Now we will use our ODE 45 solver. I will call my function as I t comma z. Z will save all my values. So t comma z equal to I will write ODE 45. Then in bracket by using iterate sign I will call my function. Then I will provide the time. I will write instance. Then I will provide my. Okay. So this will give me t comma z. So among z, okay, let's run it and see what is. Sorry, we need to write it in reverse. X is equal to y of 1 and y is equal to 3. Here, so when we run this, so we will have two matrix, one matrix with two columns. So this first column is for z, my first column is x, the second column is y. So to define my solution, I will write x is equal to z of all rows. Correct? These are all rows and only first column is z. All rows and first column will give me z, and y is equal to z of all rows, second column will be z. Correct? If we run this, sorry, z. Here z. Now if I run this, so you can see that I am having my x, y matrix. Value at last interval, last point is 0.275 into 10 raised to minus 2x. So that we are getting. So what we can further do, we can increase our this time span. We can reduce or not reduce. So let's first increase it. So if I increase the f of 1, our prediction won't be, our values will not be as accurate. You know, but it is still coming back to 1 to we significantly reduce our value of t. What will happen? It will increase our computational time. Last value 2.275. So this is how we can manipulate this. Further, we learned how to use plot function. Plot, that time for plotting my x variable with time to my on x axis is t, on y axis is x. Then I will, let's say it is in color black, it is called by t, and let's say I'm taking line width to be let's say 1. Then what I will do, I will put hold on and I will simultaneously plot my y. So I will simultaneously plotting my y variable with time. Let's say I'm keeping x label the time and y label to be, let's say I'm just writing it as a variable. And let's say I'm giving my chart title with time variation of value. I'm just writing it, just learning you how to write it now. And we run this, it both should not be black. Let's say I'm keeping it as blue, and I also need to give my legend. We write legend. My first legend is, let's say, x, second legend corresponding to y. We run this. This is how x is varying and y is varying. So this is how we solve this problem. Let's take one more problem and learn how to do it. We can easily solve our today's example statement. So the second problem is consider the following consider the following system ordinary differential equation. First one is dy1 by dx is equal to minus 1.2 y1 plus 5 y2 and dy2 by dx is dy1 minus 190.52. And given x at x is equal to 0, my y1 is equal to 1 and x is equal to 0, my y2 is equal to 0. So what is the value of y1 at x is equal to 100? So let's try to solve this. I will repeat the same procedure. Here one, here two. Next, I am just showing this because it will be useful for today's problem. dy1 by dx equal to dy1 by dx equal to minus 1.2 y1 plus 1.5 y2. My second equation is dy2 by dx is equal to 40 into y1 minus 190.5. Yes. So let's try to solve this. Here, instead of variable t, this time is they are written in as variable x. We can define our x then equal to what at what value we need at x is equal to 100 we need. So from 0 to 100 and my initial value matrix when my x is equal to 0, my y1 is equal to that. And my when my x is equal to 0, y2 is equal to 0. Then I will define dy constant dy is equal to t comma y input one end. So you always remember that function should be at end of the point, not somewhere in between, not at the starting, always in the end. Correct? My y1, what is y1? Y1 is my y of 1, and my y2 is y2 is my y of 2. Okay? Now I will write my first equation dy, first row, first column, that is equal to, I just copy this here, and it's 1 plus 1. My second equation, second row and first column, 1 by to written down our equation. Now what I need to do, I need to solve. I will write my, I'm solving it with x. Let's say my variable that is taken x comma that is equal to ODE. Here we are supposed to different ODE in it. 15 and I will write down iterate my name of the function. My pen and my initial value 5. Correct? Similarly here also my y1 in first row, I'm sorry, all rows and first column. X of all rows and first column. And my y2 is equal to x of all rows and second column. Okay? Let's say now I want to plot it. I will use my plot function. On x-axis it is x, on y-axis is y1. Let's say color is blue and my line width is line width is let's say it is 1.5. I will put I will plot my second function. Let's say x comma y2 with let's say color is green. G is represented by G. Let's say line width is let's say my line width is here also 1.1. Correct? Now I will give x label. X label is x variable. Let's say I'm just writing it, correct? And title is just giving some random thing, very different variation by with respect to x. I'm just giving it a title and giving it that. My first legend is y1 corresponding to first graph and y2 second one. So I plot this. There is some similar, not of x, to be of z. Now this value is z is saving my y1 and y2. Here we can see we have plotted it. So what is our y1 and x is equal to 100. So y1 and x is equal to near to 0, 5.7221. If we see here, what we can further do. Let's say I want to keep it like 3. My blue curve is like 3. If it's like this, what it will do? It is showing dotted line. Let's say here I want to keep like 3. So green, what it will do? Instead of 2 dots, it will be this 5. Here it will be this kind of thing. You can play with this screen. So let's say you are not keeping this kind, you're just removing this first arrow. So what will happen if you find those first point? See, that's why you can look at this blue and green are coinciding to this one. Correct? These are just points. It is not point. This is how you can play with this plot, and then you can find what kind of plot or what kind of representation is best for. Okay, so let's take now using this concept we are going to solve initial value ordinary for continuous certain reactor in series. Correct? So I will read out the problem statement from here. So the problem statement is MATLAB can be used very effectively solve a single or system initial value ordinary difference. So here that again they want to call it initial value ordinary difference. Generally when initial value is initially what is the value? Initially meaning at time t is equal to 0 or from at start. What is the value that is called initial value? And we can solve a single equation or we can solve simultaneous system of simultaneous equations. So that is called initial value problem. And using inbuilt functions. So what kind of we have till now again ordinary difference of initial value problems. We have done OD 45, OD 20, and OD. This kind of built-in function is used. Now, our problem statement is the first order chemical reaction of A converting into B type takes place in two continuous certain reactors which are connected in series. So we are having two continuous certain. So we are having two continuous certain reactors in series. So these are two CSTRs. So let's say I am adding in something, the reaction is occurring, and then again it is going into this CSTR. Correct? So like this here, A to B type of reaction is occurring. So let's say for initial value is A0, B0 at when we are starting the reaction. So at the end here we will have something CA and C. So let's call it CA1, CB1. After this here it will be CA2, CB2. So what is the use of keeping reactors in series. So we keep instead of taking one whole reactor, when we keep the reactors in series, the volume required will be less than the volume required for whole CSTR. Let's say we are having this. Let's say if we use one single CSTR of volume V, and if we go for this CSTR with series V1 and V2, then it is always V will be greater than V1, V2. So this kind of situation will be there if we are considering our reaction in series. So this is benefit. Okay. A first order chemical reaction of A to B takes place into continuous certain reactors which are connected in series. The contents in the two CSTRs are well mixed, but the reactors are not at steady state. So reactors are not at steady state. The unsteady state mass balance equation certain reactor is given. What do you mean by steady state? Steady state is when the value of, let's say, temperature, pressure, in this case, our concentration. So when it is not steady state. Steady state meaning it is not changing with time. But what is happening here? It is currently at unsteady state. So what will happen? First, A will be converted into product, and after some time, it will reach at steady state. So currently, our reactor is not at steady state. So how can we write our mass balance equation for the steady state PST? Just a minute, actually. The unsteady state mass balance equation certain reactor is given by this formula. And dCA1 by dt is equal to 1 by tau A0 minus CA1 minus A into CA1. What do you understand from this? Then the value of CA1 that we are getting is changing with time as this CA0 minus CA1 divided by tau minus, as this is the first order reaction, it is into CA1 as B is forming. So this is our reaction. As our reaction is A getting converted to B. So A is being consumed. So our reaction is mass balance equation. But for B as B is forming. So dCB1 by dt is equal to minus 1 by tau CB1 plus A into C1. Okay. Let's say if this is at steady state. So this dCA1 by dt will be equal to 0. So our equation will be CA0 minus CA1 by tau equal to K into K1. So this is something that you have learned. K0 minus K1 equal to K into tau into K. Okay. So this is how you can write it down this for first reactor. Now if we write it down for the second reactor similarly. Now what is my input for the second reactor? My input is CA1 and CB1. It's my input. Okay. For second reactor also, we can write it down as dCA2 by dt is equal to CA1 minus CA2 divided by tau minus A into CA2. And for CB2, so as already CB1, we have two reactors in series, correct? So from end of the first reactor, we will be getting something CA1 and CB1. That is being fed to second reactor. So we will have something CB1. So reaction will be 1 by tau CB1 minus CB2 plus A into CA2 plus K because B is formed. So these are the four simultaneous ordinary differences. Where CA0 is concentration of A at the inlet of the first reactor, CA1 is concentration of A at the outlet of the first reactor or at inlet of the second reactor. Correct? CA2 is concentration of B, concentration of A at the outlet of the second reactor. CB1 is concentration of B at the outlet of first reactor. And similarly, CB2 will be concentration of B at the outlet of second reactor. K is reaction rate constant and tau is residence time for each reactor. So first, what we are supposed to find? Determine the evaluations of concentrations of A and B in those reactors during their first 10 minutes of operation. The initial concentration reactor B is given as CA0 given the value of CA0. There is no, we are not mentioning anything of CB0, so we will take CB0 equal to 0. Okay, we are supposed to use C is equal to, sorry, we are supposed to use C is equal to 0.12 per minute, and O is equal to 5 minutes. Assume that the initial conditions all other dependent variables are 0. So we are only given initial condition of CA0 is equal to 20. Other than that, everything can be 0. Okay, so let's write down the code for this problem statement. Okay. So we close this thing because we are supposed to use ODE45. Let's use ODE45 problem. Okay. So let's write down what is given to us. So first, what is given to, we are given as C is equal to 0. Please develop a habit of writing minute inverse or 1 by minute unit of K. K is 0.12. Then so I am writing by capital. That is given as unit should be consistent everywhere. It is given as 5. 6 minute. Correct? And K0 equal to K0 equal to 20. 6 minute is mole per minute. Okay. So let's write down our equation first here. So my first equation is dA1 divided by dt equal to, that is equal to CA0 minus CA1 divided by T or tau. The way it is given, I am just writing it here. CA0 minus CA1 divided by tau minus K into CA1. This is my first equation. My second equation is CA2 by dt is equal to minus CB1 divided by T plus K into CA1. K into CA1. This is my second equation. Sorry, here it should be CB1. Formation of B is phosphate. Correct? Now, let's write it down for second reactor. dCA2 divided by dt is equal to CA1 minus CA2 divided by T minus K into CA2. Correct? My fourth equation is dCA2 or dCB for D. Right? dt is equal to, now here we are having some initial concentration of CB1. I will be writing it as CB1 minus CB2 divided by T plus K into CB2. K into CA2. Because A is forming sets by K. What else is given to us? We are given at T is equal to 0. CA0 equal to 20. It is 20. Correct? T is equal to 0. It is 20 moles per liter. In my CB0 is 0. And all other values also we are supposed to take. So instead of writing first our function at n, I will be writing it here only as my function is x1. That is equal to at the rate of t comma t. We will be writing one. So we have to write 4 equations, right? Like we go to the last problem. First row, first column, then second row, first column like this. My first equation is A0 minus, instead of now writing it A1, C8, CB1, CA2, CB2, I will be writing it down for P of 1 divided by P minus K into P of 1. This is my first equation. Then I will be writing down my second equation then minus P of 2 divided by T plus K into P of 1. Correct? And then we put one semicolon and I will write down my third equation. That is P of 1. Okay. Just to avoid confusion, let me write it down. That my P of 1 equal to P of 1 is equal to, let's say, this P1. P of 2 is equal to P1 and P of P is equal to P2 and P of 4 equal to. So we will write it down here. So what third equation is P1 minus P2, that is P of 1 minus P of 3 divided by T plus minus K into P2 into P of 3. Correct? This is my third equation. I will write down my last equation as CB1 minus CB2. P of 2 minus P of P of 2 minus divided by T plus, what is that, plus T into P of 3. K into CA2, so K into P of 3 plus K. So we will write down our constant or our equation. Correct? What do I need to do now? I need to call my solver. T, comma P, comma P equal to, writing it as 45. And then I will call my one. Then initial value. So what is my okay, not initial value, for time spent. So for what amount of time we are supposed to, it is not told. It is told. So for 10 minutes. So let's say I'm defining my instance equal to 0, 10. Right? I will be writing my and T0. T0 equal to P of 1 in, means P of 1 in P0 is 20, CB0 is 0, and for the second equation, 0 and 0, P1 and P2. So this we will solve and we will get our concentration. Then I will write 0. I will plot plot T comma T. Right? Will plot T comma T. Then I will use legend for it is legend as A1. First one value is my P1, and second value is B1, and my third value is P2, and my fourth value is B2. Correct? X my X label is time. Correct? My Y label is concentration. This one pricing. This one engagement. X is utility. What is the unit? Always write down. Always develop this writing. It can be one title. Variation of mission with time. Right? If you know like I will open window. So see, ideally what should happen for the first reactor, A should increase, A should reduce, and B should increase. Second reactor, both should increase. BG1 is also increasing, B2 is also increasing. So this is how we can see the effect of this value. Okay. So further what we can do, let's time copy this and let's instead of writing here this term and writing down below in terms of function, right? Writing function let's say BC equal to calling it as F1 of P comma P. Correct? My first equation will be like so this will be my first equation first equal to will be my first equation and this will be my second equation and this will be my third equation and this will be my fourth. But here what can we need to provide the value of P and one. And here I will need to one exaggeration figure. If we run this, if we are here, yeah, we I also need to find the value. A zero is equal to 20. Yes, I also need to easily
Same plot. Okay. So this is how we learn how to solve CSTR in series. Okay. So actually I don't need time here. So I can just write this as C. No, I need time. I need to put time. Okay. So we have solved the first part of our problem. So let me save this first part untitled for CSTR uh, series of part one. Okay. So now let's move ahead with the next part. What is asked? Okay. So from this plot, From this plot, we can see that, uh, sorry, where did it go? Yeah. From this plot, we can see that, see here, it is not, it is still reducing. It is not a constant value. So what we can see, or what we can say, we have not achieved steady state. So what we can do, let's just for sake of doing it, let's increase our time for 10 from 10 to 20 and see what we are getting. So see, we are achieving steady state. For this CB1, it is not constant, or it is constant but slight changes, but other values are have achieved steady state. So how can we say that our reactor is at steady state? By looking at the concentration variation. So see now also, so see here it has reached steady state after some 24, 25. Or if I will plot it for 30, I will clearly see one steady state. Okay. Wait, I have made some mistake. No, this is 20. These I need to change it as 30. Okay. So see here, it has reached steady state. So by time t is equal to 30 minutes, we are achieving steady state. Not exactly 30, before 30 only we are achieving steady state. 12.03, 12.1. So we are at steady state. Correct. So how can we find the condition for steady state? How can we do that? We can, how can we obtain the steady state? So what we can do, okay, for now I will, okay, after this, let me write it down. So let's do one thing. Let's say CA1 is equal to C of all rows and first column. Then CB1 is equal to C of all rows and second column. Then CC1 is equal to C of all rows and third column. And sorry, CA2 and CB2 is equal to C of all rows and fourth column. Correct? So let's say for M is equal to, not 4M. Okay, let's write it down in the next problem, this part 2 only, and with that complex part. So in part 2, what is told, determine the time requirement for the steady state, for the system to reach steady state as a function of both K and tau. So in the first problem, what we did, we kept the value of K and tau fixed. But now in the second problem, we are supposed to vary the both. So let's write down that part. Let's say my time is from 0 to 100. Okay, initially it was 10, but let's say now it is 0 to 100 in gap of 1. Then my CA0 I am not changing because we are just supposed to vary K and tau. So my C0 is 20 and my Y0 initial conditions. Okay, it's time joules per liter. Say it is 20,000. Let's write it down as initial condition. Correct? Okay. Y0, then K value. Let's say I'm varying my K matrix from 0.01 to 1 in step of 0.01. So this is my rate constant. Correct? Let's say my time T is equal to. Okay, so I'm here teaching you how to use this simple format. I hope you know. And when I use lean space, so okay, let's learn this. These I have already taught, but I will teach residence time. Okay, so okay, always develop this habit of writing clear all and CLC. Correct. Okay, so let's say I'm writing it 1 to 0.1 to 2. So what it will do in step of 0.1, it will increase from 1 to 1.1, 1.1 to 1.2, 1.2 to 1.3, like that. And this second thing is lean space. So what will lean space do? Let's say I am writing lean space of 1 comma 10 comma 10. So what it will do? It will between 1 and 10, it has created 10 points. Let's say I'm just writing it 5. So between 1 and 10, it will create 5 points of equal space. Okay. So here we have used our both the functions. One is normal way of giving increment, and the second one is giving using lean space, giving uh, giving the interval size. No, not interval size, giving the how many points are there, and those points will be of equal interval. Okay, so now let's move ahead. So we will have to run two loops, right? So here, let's say 4. Okay, one more thing. Let's say how many points are there? 4, 5 points we know here. But how do we know here that there are 5 points? Here, how many points are that we don't know. So what we can do? Let's say I'm defining it as A. A is equal to this. So I can write length of A. Okay, so we will get 11. So there are total 11 entries. So what I will do for I is equal to small I, for I is equal to 1 to length of T. That we already know, but let's do it in that way, or we can directly write 1 to 100. And then for J is equal to 1 to length of K. Correct? Now, what we'll do, we will define our matrix. So time, comma, concentration, I am calling it as CR. Sorry, CR, that is equal to my function is ODE 45. I am defining my function as at the rate of R. Then I need to give time span. I need to give initial condition Y0. Okay. But here there is one catch, that we need to also give uh, initial the particular value of T and particular value of K. Okay, now everything is clear. Okay. So now let's say, okay, so let's do one thing. Okay, let's do one thing. I will write down two ends. Okay, so let's do one thing. Let's write down our function first. So I'll write down my function as function f is equal to, I'm giving name as r of t comma c comma t comma k. So first time concentration, that is initial gas, t and k. And okay, so here let's first define our equation from here. So these are our four equations, correct? Now I will write down my function f is equal to the same thing that we wrote here, this term. Okay, so our equation, let's check equation. CA0 minus C of 1 divided by T minus K into C of 1, then C of 2 by T plus K into C of 1, then C of 1 minus C of 3 divided by T minus K into C of 3. Then last equation, C of 2 minus C of 4 divided by T plus K into C of 3. Correct? And here the same thing that we can also add further for understanding that what is C of 1, C of 2 and all those terms. Okay, so these we have already defined. Correct? And now I can put one and. Okay, and is already there. Okay, so here now my CA1 is CR all rows and first column. Correct? That will be my CA1. Correct? And my CB1 will be equal to CRO all rows, second column. Then CA2 is equal to CRO all rows and third column. And CB2 will be equal to CRO all rows and fourth columns. Correct? Let's say we are defining, we see, because all these CA1, CB2, CA2, CB2 will have the same length. Correct? So I will just create one matrix L that is equal to length of CA1. Okay. Now we will check for steady state. Correct? For M is equal to 1 to L minus 1, because at last point we will not have any comparison. So we will do it for L minus 1 points. N. Correct? dA dA is equal to A of M minus A of M plus 1. First point and its consecutive point. Okay. So we can say that if that difference is less than 10 raised to minus, let's say 0.01, so it is at steady state. So we can say that CA1 of that particular jth point is equal to A of M. So that is our steady state. Let's write that down. C1SS steady state is equal to this. We will put one and here. Okay. So we have checked it for CA1. Let's do this Let's just run this and see what we are getting. Let's first run this small part. Oh, it is showing some error. And here, what is it showing? Unrecognized variable CA0. Okay, we have defined CA0, right? Okay, here we have not defined CA0. So let's say CA0 is equal to 20. Yeah, okay. This is the issue here. It should be F, not F. These two names should be same. Okay. So it is okay. We are still following some issues. Okay. CA1. 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 Because our variable is not ACA. Okay. So okay. So our CA1 steady state is 19.8155. Okay. So similarly, we can do it for all values. We can check it for all. Wait a minute, it's still loading. Mhm. Let me stop this. Okay. One. Similarly, okay, let me just do one thing. It is slowing down the laptop just a minute. So let me reduce our time from 100 to 50. Okay. Now let's do one thing. It is taking time. Sorry, guys. Yeah. So similarly, we can do this for second variable, that is CB1. Okay. Let's do one thing. It's slowing down. It's really slowing down. Here, then similarly for the third. So CC1, CA2, 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 and my last is CB2. Correct? Let's put one more end here. Okay. Let's write it down as equal to, it is CA1, comma, K, comma, T. Similarly, I'm saving my variables. I'm not doing anything else. CA, CB11, okay. So I hope this is clear. Here it will be CA2, comma, K, comma, T. And my last is saying CA, sorry, CB22 of I, colon, comma, I is equal to CB2, comma, K, comma, T. Correct? And we will put one end. Okay. Now let's try to run this part. Okay, there are some errors. Okay, here these two end. Okay, I hope it is clear now. So if we run this, yeah, here it should be not CA1, but it should be what we have given the name. It is CA1 underscore SS. Okay, so it should be CA1 underscore SS. Okay, CA1 underscore this underscore SS. Okay, now it should not cause any issue. Yeah, so see, it is now running without any error. So if I open this CA11, see, this is a huge list available. So we have learned how to estimate steady state. So further, what we can do? So let's say we are having three variables now. We are having K, T, and concentrations. So let's try to plot a 3D plot. So let's say I'm writing it down as figure 1. So to plot a 3D plot, okay, let me search plot 3D in help section and let's see what we are getting. Okay. So see here, I want 3D plot. Okay, these contour plots, 2D and 3D. Oh no, not contour plots. Sorry. We need to press one back. So where can we get that 3D plots? Yeah, this thing. So the command is plot 3 x comma y comma z. Okay, so it will create one 3D plot. So let's try to create one 3D plot. So plot 3 x comma y comma z. Okay. So plot 3, then x is k, t, and let's say it is CA1 underscore steady state. Then let's say line width is 3, just random value. My X label is K, Y label is T, and Z label is concentration. Concentration in units of moles per liter. Okay. And let's say my title of this whole thing is CA1 versus T versus K, as it's a 3D. So let's try to run this and see what we are getting. We'll be getting one 3D plot. So see, we are having one plot. So I will open it in a new line, new window. So see, this is how K is varying. With K, my concentration is varying. With residence time, my concentration is varying. This is with both the scenarios, we can see the variation of concentration. So this is 3D plot. So further, similarly, what we can do, we can plot the same thing for CB1. So let's do that. So I will use figure 2 and I will write it down here as CB1. And let's try to run it. Okay, I have made a mistake. I will put stop. It is CB1, correct? So we are having plots. Oh, something is open. Oh, some matrix y0 and k. Let me just check it. We can put one semicolon. Yeah, here we need to put one semicolon. Because it is printing everything and that we don't need. Okay. Let's just rerun this. So see, both the plots we have. Let's open these both figures. Okay, let's open this first one first. And then this second one. First one is like same only. There is no change. So this is second one. So CB1 is increasing. See, so if I just put it, okay. So you can select a point. And you can see when tau is equal to 0.67, sorry, when k is equal to 0.67 and tau is equal to 7, my CB1 is 17. Okay. So this is for CB1. Similarly, let's do it for other variables also. It will be really not a good idea to plot all three charts in a same plot because it's already a 3D plot. You can do it. And CA2. And similarly for CB2. Is C2. So let's try to run this code. So what I will do now, I will just running. Okay, so this is figure 4. Oh, I have not changed the name of the figures. Yeah, I have changed. Okay, so this is CB2 versus time. This is CA2 versus time. This is CB1 and CA1. These are all four plotted with respect to rate constant and time. What further we can do? We will obtain more number of data points. Let's see if I'm increasing it from 50 to 100. Okay. So it will take some more amount of time to run the code. So you can clearly see it's taking longer amount of time. Okay. So, okay, let it load. Yeah. So we have now time is more, but this key and tau are same. So let's do one thing. Let's from 0.01 and let's go from 1 to 40. Okay. So it's going to take, okay, let's do one thing. I am pausing it. Let's just run it for 50 minutes of time. And let's just see what we are getting. It will take some time to run, but we will have a good feel of these plots. See. Range 0 to 1 and 0 to 40. Okay, so this is how you can plot a 3D plot. So what we have learned from this problem, first, we have learned how to use ODE45 solver. Then second thing, how to write down our own function. Then third thing, how to estimate if our process is at steady state or not. And then the fourth thing we learned how we can plot one three-dimensional chart. Can we plot a contour chart? Let me try it. I'm just not sure. Contour. I'm just willing to see if it works. Wait a minute. I guess I'm writing it in a wrong spelling. CON. Okay, CONTOR. Okay, sorry. I just want to see contour plot. So it is also XYZ. So let's just try to plot one contour plot and see what we are getting from this contour plot. So just this thing instead of plot 3, I will use contour. CONTOUR contour. Okay. I don't know if it will work or not, but let's just try it. Format is same contour of x comma y comma z. So that's why I want to try it. It is for matrix, so contour won't work. But okay, we have learned how to use ODE45 solver, how to estimate steady state from plot also, and from mathematics. Then we learned how to write down our own function. And the fourth thing we learned is three-dimensional plot. So till now, what we have covered ordinary differential equations, initial value problem, and those all were first order differential equations. Correct? So what do you mean? Again, I am telling what is initial value problem. Initial value problem is meaning when something is defined as t is equal to 0. And the next set of problem that we are going to see right now is The next set of problem is boundary value problem. So what is boundary value problem? Boundary value. I'm sorry, why? I don't know why it is happening like this. Uh, okay, let me write it down here. Boundary value problem. Okay, so let's see. This is one surface. From here, heat transfer is occurring via conduction. Let's say I'm just specifying it conduction. We don't need to say it actually. But let's say I'm saying it conduction. Sorry guys, I don't know what's happening. Yeah. So boundary value problem. Let's say heat transfer is occurring and you know that, and at this end, my temperature is, let's say, some X value, and here this end temperature is Y. And we need to solve this kind of equation. So what is there? We know the value of temperature at both the boundaries. So that's why it is called boundary value problem. So there are two conditions, so our equation will be of second order equation. So it will be something called d square d by dx square kind of equation, wherein initial value problem we have only one thing, that t is equal to 0. We are given some condition, let's say y is equal to y0. So we are having equation of dy by dt is equal to something. But here, as it's a boundary, and boundary for just this example, there are two boundaries at t is equal to x and t is equal to x is equal to this boundary, and at this boundary we can say x is equal to 0, my t is equal to tx, and my x is equal to at end of length my temperature is t is equal to ty. So these kind of problems are called boundary value problems. Okay, so it is more complex than this, right? Because this is second order differential equation and we don't know how to solve this kind of equation. Okay, so let's try to learn this, and I will be teaching this part through this previous year's assignment questions. Okay, so the first question is a boundary condition that specifies the value of independent variable at a given point is called which boundary conditions. So there are various kind of boundary conditions that I will teach you from a book. So let me open the book. That is chapter 5, page number 104. Okay, so we will see various kinds of boundary condition in this particular question. Okay, so there is first boundary condition that is called Dirichlet boundary condition. So what is Dirichlet boundary condition? Let's read it. A boundary condition is said to be a Dirichlet condition when the value of the dependent variable is specified on a surface. So only value is specified, nothing else. If the value of the function is uniformly 0, we have a homogeneous Dirichlet condition, else it is non-homogeneous. Let's not worry about this homogeneous and non-homogeneous part. So the condition will be in this form: u is equal to f on the surface. Correct? The problem that I showed you. So here they have given one example, that consider a fluid flowing through the stationary flat plane. So here it is flowing. If the surface of the plate is at y is equal to 0, no slip condition, then we can see that at y is equal to 0, u is equal to 0. So this kind of condition is called Dirichlet boundary condition. Another example is given as, consider a sphere of radius r immersed in a well-stirred fluid at temperature Ta. So the agitation in the fluid lowers the resistance to heat transfer in the fluid, and the temperature of the surface can be taken as the temperature of the surface of the sphere can be taken as equal to Ta. So what is this condition? At r is equal to r means outer surface of sphere at r is equal to r, my temperature is Ta. So this kind of condition is called Dirichlet condition when we are specifying only value. Value of what? Value of dependent variable at surface we are specifying it. There is one more problem. A similar condition arises for the concentration on the surface of catalyst pellet in a fluidized catalytic reactor. This kind of same condition is there. Further, for the low mass transfer resistance to the agitation, the surface concentration C is spherical catalyst is C is equal to 0. So this is just condition at R is equal to R. Something is specified. So this kind of boundary conditions are called Dirichlet boundary conditions. Now let's have a look at second kind of boundary condition. Those are Newman boundary condition. So a boundary condition where we specify the outward normal derivative on the surface, it is called Newman boundary condition. So here we are not specifying the value of dependent variable at surface, but we are defining the normal derivative on the surface. So this kind of condition where we are defining normal derivative, it is called Newman boundary condition. Okay, so the condition is in form minus n into gradient of u is equal to f. Okay, let the flux of heat transfer through the curved surface of a solid cylinder is Q. The heat flow occurs inside the cylinder due to the conduction. So my heat transfer Q will be equal to minus K del T by del R at my outer surface R is equal to R. So here we have not defined what is the value of Q or what is the value of T at R is equal to R, but we have defined gradient of that dependent variable T. So that's why minus K dt dr is equal to 0. This kind of condition is called Newman boundary condition. In a general problem, Q does not have to be constant and can vary with the angular position theta as well as axis direction Z and surface R. Okay, the heat flux across an insulated surface is 0 because surface is insulation, so there is no heat loss. Okay, so in that case, we can write gradient of T is equal to 0. So gradient of T is nothing but del T del X is equal to 0. So this kind of condition is also called Newman condition. Okay, one more problem. Consider a fluid flowing as a film of constant thickness down an inclined plane. This figure 5.3. From here, our fluid is flowing. Okay, this is inclined plane that y is equal to 0. Here u is equal to 0, y is equal to h, du dy is equal to 0. The vanishing of the shear stress on the free surface of the film yields this Newman condition of del u by del y is equal to 0 and y is equal to h. So at surface, we have defined normal derivative. So it is called Newman boundary condition. A zero mass flux across an impermeable surface at x is equal to 0. So del C by del x is equal to 0 at x is equal to 0. This is called Newman condition. So till now we have looked at two boundary conditions. One is Dirichlet boundary condition, where at surface dependent variables value is defined. And second, Newman boundary condition, where at surface the derivative is defined. Normal derivative is defined at surface. So that is called Newman. Now the next one is Robin boundary condition or mixed boundary condition. So in many problems, a combination of outward normal derivative and a variable at the surface is defined. So one thing is at, let's say x is equal to 0, we have t is equal to something, and at x is equal to r, we have del t by del r is equal to 0. That kind of condition where it is mixture of Dirichlet and Newman boundary condition. So that is called, by default it should be mixed because it is the mixture of Dirichlet and Newman, or it is called Robin mixed boundary condition. Okay. So this problem, yeah. Consider a rectangular slab 0 to A. Let the two faces at x is equal to 0 lose heat to the ambient at TA by Newton's law of cooling. It implies the rate of uh, heat transfer is proportional to the temperature difference Ts minus Ta. Heat is transferred to the surface in a slab by conduction, and at x is equal to a, n is the positive direction. So see, so at x is equal to 0, here we can write minus k del t del x plus h into t is equal to h into ta. X is equal to a or x is equal to 0. So this is called Newman boundary condition. Sorry, this is called Robin mix boundary condition. One more condition, this condition we have defined. Okay. For this equation also, it is solved. And for Cauchy boundary condition. So these Cauchy boundary conditions occur usually in solving hyperbolic equations. These you don't need to learn what is called hyperbolic. This we will see in upcoming class, hyperbolic PD. Both values of dependent variable and the value of its derivative are specified at the surface. So we are told that as t is equal to 0, u is equal to something, and that du by dt is also given. So this kind of condition where it is with respect to initial condition, it is called Cauchy boundary condition. And this is only with when we are dealing with hyperbolic partial differential equation. So let's take our problem. A boundary condition that specifies the value of independent variable at given point. So it is, what is it called? Dirichlet boundary condition. Okay. So what is given in option? Robin mix. Robin mix is combination of Dirichlet and Newman. Cauchy is for initial value problems. Newman is only derivative. So there is no option of Dirichlet. So the correct answer is D. None of this. Okay. I hope this part is clear for everyone. Next question. Okay. The BBP4C and BBP5C in The BBP4C and BBP5C inbuilt solvers in MATLAB are used to solve boundary value problems. These solvers are based on which method? So let's check what is BBP4C and BBP5C. The correct answer is it is based on finite difference method. So we will learn what is finite difference method in today's class only. So I will just write it down. BBP4C. Okay. I guess they will not have specified it. They have not specified. Wait, let me check difference. This thing. No, it is not specified, but the answer is finite difference method. So let's try to understand what is finite difference. Okay. In finite difference method, I find u at z plus delta z is equal to u of z plus del u by del z dz du by dz delta z plus 1 by 2 factorial del square 2 by dz square and delta z whole square, then 1 by 3 factorial del cube u by del z cube into del z whole cube, like that. And let's say I'm writing it now backwards. Z, I want to find it at backward point. Just a minute, guys. Let's say I want to find it at z minus delta z. So it will be u of z minus delta z is equal to u of z minus duz by dz into delta z plus 1 by 2 factorial d square u by dz square into delta z whole square minus 1 by 3 factorial d square d cube u by dz cube into delta z whole cube up to n. So if we add these two, if we just write down our first equation, rewrite it. So my du by dz will be equal to u of z plus delta z minus u of z divided by delta z. So this is called forward difference approximation. Further, if I write it down, I find du by dz from this problem. So it will be u of z minus u of z minus delta z divided by delta z. So this is called backward difference approximation. So it may be noted that the errors in forward and backward difference approximation are of order delta z. Now alternatively what we can do, if we add these two equations, so this term will be cancelling out. So if we need to find du by dz, we don't need to add, but we need to subtract these two equations. So if we subtract these two equations, we get du dz is equal to u of z plus delta z minus u of z minus delta z divided by 2 into delta z. So here the order of error is in the power of delta z square. Correct? So this is called central difference, where we are calculating derivative at both the points, at forward points, that is z plus delta z, and at backward point, that is z minus delta z. So this kind of problem, this is called central difference. So from this we can also calculate d square u by dz square, that is second derivative. So central difference is mainly used because of its accuracy and order of error in delta z. So this is how we can calculate d square u by dz square also. So this one is called, yeah, these are central difference formula. Okay, so this both BVP 4C and BVP 5C, I'm sorry, these both BVP 4C and BVP 5C works on the method of finite difference method. So our correct answer is B. Okay, let's move ahead. To use the MATLAB ordinary value problem solvers, the higher order ordinary differential equations are reformulated to a system of first order ODEs. Is this correct or not? This is correct. We will take a problem. We will not solve it for today's lecture, but I will just show you one solved problem for this BBP4C. We will solve this boundary value problem in next class. So let's say they have solved this particular differential equation, that is, so see here, it is a boundary value problem. The problem statement says that d square y by dx square, let's say it is d square y by dx square plus y is equal to 0. And we are given that x is equal to 0, y is also equal to 0, and x is equal to pi by 2, y is equal to 2. So first, this is Dirichlet boundary conditions, correct? And what we are doing here. So see, let's read it down what they have written. We will try to solve this problem. So write a function that codes the equation. Usually use the substitutions y1 is equal to y. So call y as y1. This one is my y1. Okay, I won't be able to write it here. So my y is y1 and y2 is my y prime. Y2 is my y prime, correct? So my y1 will be equal to y1 prime will be equal to my y2, and y1 prime will be equal to y2, and y2 prime will be equal to my negative of y1. So this is my equation. Y2 prime is equal to minus y1. So what we did, we converted this d square y by dx square in term of this y prime. Okay. So if we write it here, function dy dx is equal to bvp function x comma y. where we defined my first equation as y2 and my not first equation. Here we can't write it down in whole equation. So my first is y of 2 and second is minus y, and minus y is my minus y of 1. So this is how we can define our, or we can formulate our equation. Similarly for boundary conditions, so what we did, we converted our second order ordinary differential equation into first order equation. Similarly, let's take the second problem. So here also what we need to do, y1 is equal to y, y2 is equal to y prime. So my y1 prime will be equal to y2. So y of 2, and my second equation will be minus 2 divided by x, y prime, that is my y2, y2 minus y of 1 divided by x raised to 4. Correct? So what we did, we converted our ordinary first or second order differential equation into first order equation. Okay. So we will solve this problem. We will try to do this for next week, not for today's week, because it is only 25 minutes left and we are just seeing the theory currently. So the correct answer is true, that to use MATLAB boundary value problem solvers, the higher order ordinary differential equations are reformulated to a system of first order differential equation. Okay, so the correct answer is true. Now next problem. The correct formula to approximate the derivative of f of x for a dataset consisting of I is equal to 1 to n by central difference. So what did we do for central difference? We write it down as u of z plus delta z is equal to u of z plus du by dz into delta z, and u of z minus delta z is equal to u of z minus du by dz into delta z. If we perform subtraction, so minus minus plus, so this will be cancelled out. So it will be u of z plus delta z minus u of z minus delta z divided by 2 times delta z is equal to du by dz. So let's say z plus delta z. So it is the next step. So it is f of I plus 1. It is f of I minus 1 divided by 2 times delta x is equal to df by dx. So our correct answer is B. Sorry, our correct answer is this C. df by dx is equal to f of I plus 1 minus f of I minus 1 divided by 2 into delta x. And what is the order of error? Order of error is delta x, the difference square. While in forward difference, what it will be? It will be simply order of delta x. Correct? So this is the formula for central difference. Which one is for forward difference? This one is for forward difference. Correct? And here this one I to I minus 1 we are going. So this is for backward difference. And this is also for central difference, but it is not df by dx. It is d square f by dx square. Okay. So this thing you need to know. Okay, let me rub this thing. Okay. So next problem. Okay. Let's not solve this problem right now. Let's check this sixth problem. The steady state material balance. This problem 5 will solve in next class. Question 6. The steady state material balance for diffusion and reaction in a spherical catalyst pellet leads to the following boundary value problem. D square C by dr square plus 2 by r dc dr is equal to phi square into c raised to n, where c is the dimensionless concentration, r is the dimensionless radial position, phi is the Thiele modulus, and n is the order of reaction. The boundary value conditions are at r is equal to 0, dc dr is equal to 0, and R is equal to 1, C is equal to 1. Choose the correct option or options related to this problem. So the problem has Dirichlet boundary condition at R is equal to 0. Okay, let's first remember what is Dirichlet condition at x is equal to 0, t is equal to tx. This is called Dirichlet condition. The value of dependent variable is given at particular surface. And what is Newman boundary condition? Let's say at x is equal to 0, dt by dx is equal to 0 is given. So this is called Newman boundary condition. So let's try to relate it with this. So what kind of boundary condition is this? At r is equal to 0, dr is 0. So this is called Newman boundary condition. And this thing at r is equal to 1, c is equal to 1. So at surface, the value of dependent variable is given. So this is called Dirichlet boundary condition. Okay, so let's try to find out the correct statement. The problem has Dirichlet boundary condition at r is equal to 0. At r is equal to 0, is it Dirichlet boundary condition? No, it is Newman condition. So this is wrong. The problem is Dirichlet boundary condition at r is equal to 1, and as r is equal to 0, this is Dirichlet, so this is correct. The problem is Newman boundary condition at r is equal to 0, this is correct. And the problem is Newman boundary condition r is equal to 1, so this is wrong. So we have learned from this problem the application of Dirichlet boundary condition and Newman boundary condition. And what is together this is called Robin mixed boundary condition. Okay, because in one problem both the boundary conditions are defined at r is equal to 1, the value of dependent variable, and r is equal to 0 its derivative. So this is whole called a Robin mixed boundary condition. Next problem. Okay, this PVP forces follow we will see next class. Question 8. The possible mechanism of heat transfer in liquids and gases is what is possible mechanism of heat transfer in liquids and gas? So for liquids and gas, it is both conduction as well as convection. Okay, so for gases it will be mostly convection, but for liquids, for solids it is mostly conduction, and for liquids and gases it is mostly convection. Okay, but sometimes it can be conduction for liquids. So the correct answer is C. How can we define conduction? Q is equal to minus K dt dx. Convection, how can we write Q is equal to H A delta T? Correct? So this is called Newton's law of cooling, and this is called Fourier's law of conduction. Okay. So the correct answer is C. Okay. Now next problem. The temperature distribution in a large thin plate with uniform surface temperature will be. So what we can write? We can write it as Q is equal to minus K dt dx, and from this we can derive that d square t by dx square. But here it is at steady state. Equal to this term won't be there. This term won't be there as it's steady state. So d square t by dx square is equal to 0. So dt by dx is equal to some constant. So t will be some constant into x plus c2. So this is how it is varying. It is varying linearly. So our correct answer will be C. Sorry, the correct answer will be D. The variation is in linear format. Okay. It is the same question. Okay, this question. Identify the incorrect statement from the following options regarding assumptions of Fourier's law of steady state one-dimensional heat flow. So let's first see it in detail. Just give me a minute. So for this part, so see, this is our Fourier's law. Q is equal to minus Ka dt by dx. What is it saying? The rate of heat flow by conduction through a uniform material is directly proportional to the area normal to the direction of heat flow and the temperature gradient in the direction of heat flow. So my Q is proportional to A into minus dt dx. So Q is equal to minus Ka dt dx. Why minus sign is there? Because when we are going from this point to this point, temperature is reducing. That's why the sign is negative. So when we derive this equation, what is written? There is no internal heat generation, correct? We are not saying that there is some heat is generated from body itself. Then boundary surfaces are isothermal, so there is no heat loss. Then third is material is anisotropic. So this is completely wrong. Material is isotropic, meaning in all direction value, it is in all direction the property of materials are same. If it is anisotropic, then in x direction its conductivity will be different, in y direction its conductivity will be different. So the material is not anisotropic, the material is isotropic, and the option D is constant temperature gradient exists. So this is also correct. So our answer is C. Material is anisotropic, so that is completely wrong. The material is isotropic. Okay. So the next question, negative sign in heat conduction equation indicates heat always flow in the direction of lower to higher temperature. Is this clearly correct or not? This is absolutely. Does heat flow from lower to higher temperature? No, heat never flows from lower to higher temperature. Heat always flows from higher to lower temperature. So see, here let's say my temperature is 50 and heat is flowing. So by reaching here, it should reach some 30. So we are flowing from higher to lower temperature. And we are writing delta T in terms of T2 minus T1, that is 30 minus 50. So here it is coming out to be negative, or delta T will always be negative. That's why we write Q is equal to minus K dt dx. Why minus? Because this delta T is already negative. Dt is changing, dt is reducing with increase in x. So that's why we are putting a negative sign. So this is wrong. This can't be true. This can never be true that heat is flowing from lower to higher temperature. Okay. Option B is heat always flow in the direction of higher to lower temperature. This makes all physical sense. Option C is there is no heat flow. So this cannot be true and data is no. So the correct answer is heat always flow in the direction of higher to lower temperature. Okay. These kind of questions are generally asked in your GATE exams. At least in our time, it used to be. Now, I don't know. These are very fundamental questions. Question 13. The thermal conductivity represents the amount of heat conducted across a unit area when temperature difference is 1 Kelvin. Let's see this. So Q is equal to minus Ka dt dx. So what is K? K is Q per area per dt per dx. Okay. So here what they are saying, the amount of heat conducted across a unit area when temperature difference is 1 Kelvin. Till here it's correct, but there is no mention of dx. So this is wrong. So what should be the correct statement? It is across a unit area and through a unit difference. This thing we need to mention. So if we its unit is watt per meter square. What is the unit of K? It is watt per meter Kelvin. Quantity of heat passing through a quantity of material of unit thickness when a unit temperature difference is maintained across the opposite. A quantity of material, the thermal conductivity is the quantity of heat passing through a quantity of material of unit thickness with unit flow area in a unit time when a unit temperature difference is maintained across the opposite faces of material. So there is no here, there is no mention of unit thickness. So that's why this sentence is not true. My 14th question, mark the matter with the least value of thermal conductivity. So from our common sense, what should be the value? Liquids generally highest thermal conductivity is with solid, then liquids, and then gases. So here solids, liquids, and this is gas. So this should be with least thermal conductivity. We can also check the value of thermal conductivity. Let me just check it. So thermal conductivity of air is 0.025 watt per meter Kelvin. So let's just mention these values. This is 0.025. Correct? Okay, what is the thermal conductivity of water? So that will be something good, zero point 0.6 watt per meter Kelvin. Correct? Then thermal conductivity of S material. It varies between 2 and 3. So let's say it is 0.2. And of window glass, it will be significantly good value. That is 1. Okay, so we can see that this is highest, then least, then decreasing, and this is air is having the least value of thermal conductivity. So our correct answer will be A. Here you don't need to know the values actually. It is just logic that solids have highest, then liquids, and then gases. Okay, so correct answer is A, air. 15th, most metals are good conductors of heat because of what metals is having. Let's say sodium metal. So what is it having? 1s2, 2s2, 2p6, and 3s1. So sodium is metal, so there is one free electron, and this free electrons uh, work as a because of these free electrons available in most of the metals. This is just sodium. We can take more number of magnesium, aluminum. Aluminum is mostly useless alloy, but aluminum is having 2s2 and 3s2 and 3p1. So they are having free electrons. So because of the availability of free electron in most of the metals, so free electrons carry the heat. So because of that, those are good conductors of heat. So our correct answer is B, free electrons. Okay. So in today's lecture, okay. So in today's lecture, what did we learn? Let's list down what did we learn. So first, we learn ODE 45 for initial value problem. So we learned how to use solver ODE45 that mainly works on RK4 method. We also check ODE23 and ODE15S. Then further we learned how to write a function, correct? Then we learned how to plot our data and make and how to plot our data and present it in good way. This is what we learned. Then after that we took one example of continuous third tank reactors in series with order of reaction n is equal to 1. That we learned how to estimate steady state. This is what we learned in today's class. And then we learned three-dimensional plot. So that is plot 3, MATLAB inbuilt function. This is what we learned for initial value problem. These three things we revised from last week's lecture, and then in today's lecture we learned CSTR in series and how to estimate steady state and how to plot a three-dimensional plot. Further, further what we learned, further what we learned, further we learned about boundary conditions, where one is Dirichlet boundary condition, where the value of dependent variable is given at surface, let's say at x is equal to 0, t is equal to tx. This is called Dirichlet boundary condition. That is Newman boundary condition, let's say at x is equal to 0, del t by del x is equal to some value of, let's say, del t by del x is equal to 0. Let's say this. Then we learned Robin mixed boundary condition, where it is the combination of 1 plus 2, and one more boundary condition that we learned was Cauchy boundary condition. Then further we learned about finite difference method. Finite difference. So the first one is forward difference, where you take the value of function at I plus 1 and at I. Then second thing we learned is backward difference, when we take the difference of fi plus 1, I minus 1 and f of I. And third thing that we learned is central difference, that is at fi plus 1 and fi minus 1. So this thing we learned, and we saw that order of error is delta x whole square in case of central difference method. Then we just had a small look on BBP4C and BBP5C function. These two functions we are going to use in our next problem, and we are going to solve a more number of problems using by solving boundary value problems. So in next week, we are going to check these two problems. The first problem is heat transfer through a cylindrical rod, where we are given the temperature at x is equal to 0, it is t is equal to Ta, and x is equal to L, it is t is equal to Tb, and it is heat transfer is both conduction and convection, and the reduced equation is this: d square t by dx square is equal to minus h t infinity minus t. This we are going to solve, where it is a Dirichlet boundary condition. And the second problem, that first one also you have learned in your heat transfer course, and second problem is reaction in a catalyst 4, where this equation d square Ca by dx square is equal to k by dab into Ca. This we are going to learn, where the condition is at x is equal to 0, Ca is equal to 1, and x is equal to L, dCa by dx is equal to 0. So this is Newman boundary condition, where x is equal to 0 value is defined and x is equal to L its derivative is defined. So these two problems we are going to have a look in next week's problem. So thank you so much. And we will meet on next week. If anyone is having any query regarding to your assignments or regarding to anything else regarding related to study, please feel free to write me an email on this email ID. I will try to respond to your queries as soon as possible. So thank you so much, and we will meet on next week.